unsaturated hydrocarbons, right? Because unsaturated, I pulled my hair. Unsaturated means what? The lack of, right, and what are we lacking in an unsaturated hydrocarbon? Hydrogens, right? And what takes the place of hydrogens on our molecule? Right, what are we replacing hydrogens with in an unsaturated compound? Oh man, maybe that one. All right, so hydrocarbons. What is a hydrocarbon? What is carbon? I'm just gonna keep going back until we get to where we remember things. Right. So hydrocarbons, right? Based off of the name, what do you think a hydrocarbon is? Probably only going to contain what two atoms? Right. Only. Right, this is an organic molecule of only H and C. Right. And saturated hydrocarbons. Bless you. This meant what? Yeah, basically every spot where we can have a hydrogen, right? And each carbon wants to have how many bonds? 4 bonds, right? That's filled with a hydrogen, right? So it means every spot that can have H has H. And unsaturated means that not every spot that can have an H has an H, right? There's some spots that we don't have a hydrogen there. And if we only have carbon and hydrogen, what's the only way we can eliminate hydrogen in these cases? Yeah, if there's a double bond, right? So saturated carbon, unsaturated hydrocarbons have double or triple bonds. And so this will eventually lead to, if you talk about like saturated versus unsaturated fatty acids, fats and oils and stuff like that, this is what that's related to. It's basically in these long carbon chains on these molecules, is there a double bond or a single bond, right? So this is when we're talking about unsaturated versus saturated molecules. This is what we're highlighting. You know, is there double bonds in the structure, or is it all going to be sp3 hybridized carbons? Right, and the existence of these changes the physical properties and their reactivity a lot. So today we'll go through some of the reactions for alkenes and alkynes, and we'll see that you know, the double bond allows for more reactivity of these compounds. Alkanes and saturated hydrocarbons a lot of the time were relatively inert. I mean, they don't really react with a whole lot of stuff. We just went through the one halogenation reaction, right, where you bubble, you know, some halogen over a saturated alkane, and you'll start replacing the hydrogens with the you'll start replacing hydrogens with whatever the halogen is, right? So this is the hydrocarbon, and then today we're finishing up discussing unsaturated hydrocarbons, and we'll talk a little bit about aromatic hydrocarbons too.
You just said the last lab that we did was the exception of the saturated hydrocarbons?
It was the exception. How do you mean?
Did you? I'm not sure if I heard you right.
Right now?
You just said the last lab we did, and you said something about bubbling, and that was the exception to the stability.
Oh, no, I said last time we talked about reactions. We talked about reactions of alkane, and it was bubbling halogen gas or some sort of halogen in the solution with the alkanes, and you'll replace the hydrogens with whatever that halogen is. So you can halogenate an alkane. But really the reactions that are involved without getting for a simple hydrocarbon or a saturated hydrocarbon, there aren't that many reactions that we will go through. But that halogenation is important because a lot of times that's a starting point for almost a lot of other reactions. All right, so let's go over this. Did we do this last time? I don't think so, right? So draw the cis and trans isomer for 2-bromo, 3-chloro, 2-butene, right? So this will be good practice to remind us of our naming conventions for organic molecules in general, isomers of alkenes, and you know, what kind of isomer is this? And then also the naming conventions for alkenes. So I'm going to draw that right now. And I'm not going to label. I'm going to draw 2 different I'll just start with one actually. So we have 1, 2, 3, 4 because we have 2 butene, right? So that's how we know we have 4 carbon atoms here. And then on the second carbon, what else are we gonna have? A bromine, that's correct. So we'll have a bromine there. And then on the third carbon, we'll have a chlorine, right? So we'll have a chlorine here. All right, and so I double check, 2 bromo, we have that, 3 chloro, I just added that, 2 butene, 1, 2, 3, 4 carbon atoms, and then a double bond that starts on the second carbon, right? So the structure checks out with the name, and it says draw the cis and trans isomer for this molecule, right? So which isomer is this gonna be? This will be a trans isomer, right? Because we have the alkyl groups, right, on opposite sides of the double bond. So this is going to be trans. And what would the cis isomer look like? A horseshoe, is that what you said? Yeah, kind of like a horseshoe a little bit, right? All we're gonna do is we're just gonna flip the position of, let's say, the 4th carbon and the chlorine right here. So this will look something like this. Chlorine and then bromine. Now we have a trans isomer because a cis isomer, because both of the alkyl groups are on the same side of the double bond. And we can say the same side of the double bond because does this bond rotate at all? I don't know, I went into probably a little bit too much details to what a pi bond actually looks like. But remember I said that for a pi bond, it's basically like you have 2 overlapping p orbitals that kind of extend over the sigma, the single bond, right? And that's what creates the pi bond. And because you have that above and below the single bond, it restricts rotation, right? And another way we can remember this is what's the geometry of that carbon right there? Trigonal planar, right? Which means that this all lies within the same plane, right? We can't have, if these are both supposed to lie within the same plane, you know, if we were to rotate that bond at all, that wouldn't make sense because then they'd be out of plane of each other. This whole molecule is all lying within the same plane because this is trigonal planar and that's trigonal planar. So there's no rotation about pi bonds or double bonds and triple bonds. There's no rotation about them, right? And you know, maybe this will a little bit is if we think about these are the different potential p orbitals and it's a bond between 2 carbon atoms like this. The double bonds, right, is an overlap of these p orbitals, right? And because it's, you know, an interaction above and below the carbon atoms, it doesn't allow rotation, right? It's if you had 2, I don't have the molecular model K here, but it's like if you had 2, I think I drew that to the wrong. Sorry, I drew this to the wrong, between the wrong lobes. So it'd be, oh no I didn't, I drew it between the right ones. It just has to go below, right? So these would be like the perpendicular p orbitals and the ones that the double bond is just between the vertical ones. And so you can imagine, yep, it applies to both trans and the cis isomer, right? So this is the pi bond or the double bond is always going to be an overlap of unhybridized p orbitals, right? Remember we talked about the hybridization of these orbitals. This pi bond is the overlap of unhybridized p orbitals. And that, like I said, I'm not going to be explicitly testing you on this, but that's why we have these specific stereoisomers is because we can't just flip the carbon atom around, right? With single bonds, you know, those bonds are allowed to rotate with respect to each other. They can move around and they're bendy and floppy in space, whereas these double bonds are more rigid, right? And they're rigid because of this overlap between the p orbitals that restricts rotation about these bonds. So if you restrict rotation, you kind of restrict the overall structure of the molecule. This is a very simple molecule, but you know, if you have a long chain in a protein or something like that, that'll restrict the structure of the protein. And with proteins, we're gonna see that that structure and function go hand in hand. All right, any questions on this? Was everyone able to get to this answer with the naming? Right, so this is good because for, you know, the rest of the organic chemistry portion, this is going to be, important for understanding the other reactions and stuff that go on. Okay, so remember I mentioned the alkenes and unsaturated hydrocarbons in general are more reactive than saturated hydrocarbons, right? So these are alkenes are more reactive than saturated hydrocarbons. And that's basically because the existence of this double bond has more electron density there. It can participate in different interactions with other atoms and molecules. And so the different reactions that we'll talk about, and we're not going to go through the mechanism of how these reactions actually work, what atoms are attacking what. We're just going to basically set up a predict the products type situation. I give you this molecule, and it's going to go through in a hydrogenation reaction, predict what the product is going to look like, right? So we're going to identify where the alkene or alkyne is on the molecule, and then that's going to be where the substitution or addition happens, right? So the three reactions are going to be hydrogenation. When I say hydrogenation, what do you guys think that we're going to be adding? These are all called addition reactions, so we're adding stuff to the molecule. What do you think we'll be adding? Yep, we're going to be adding hydrogen. If we have an addition of a halogenation, another addition reaction, we're going to be adding what to the molecule? We're going to add some halogen there. And if we have hydrogenation, right? So hydrogenation, this is actually spelled wrong. I was like, what? This is a hydration. Sorry about that. A hydration reaction. If we have a hydration reaction, what do you guys think we're going to be adding to the molecule? Water, right? Hydration, we're adding water, right? So this is going to be plus H2O. And this one, I'll just, preface it by saying it's not necessarily going to be adding a water molecule to the molecule of interest. It's going to be adding an OH and an H, right? Because we can't add a water molecule because H2O, oxygen only likes to have two bonds. If you put another bond to it, it'll be positively charged oxygen. Doesn't like that. So we're going to be adding an OH to one part of the molecule and an H to another part of the molecule, right? And together we've added water, but it's an individual addition of hydrogen and hydroxide or an OH group. Hydroxy group is what we call that.
And all of these would react to the double bond.
And all of this is going to be reactions with alkenes, and so we'll talk about what that looks like. All right, so the hydrogenation of an alkene, this is going to require a nickel or platinum catalyst. And basically all you do for a hydrogenation reaction is you're going to bubble hydrogen gas, and then we have nickel or a platinum catalyst. And we're going to start with some molecules. So let's say we start with butene, 2-butene, like we just had right there, right? Where are the hydrogens on this butene? Well, there's going to be one on each double bond, right? So I'm going to draw them right here. And then where else do we have hydrogens on this molecule?
3 on the end.
Yep, 3 on each end, right? Because carbon wants to have how many bonds? 4 bonds, right? So we have 3 on each end. And so with the hydrogenation, it's an addition reaction, and we add stuff by getting rid of the double bond, right? So when we have the catalyst, the double bond's going to interact with that metal in some fancy way that we're not worried about. And then that double bond is going to be eliminated, and when that double bond gets eliminated, it opens up 2 spots for hydrogens, right? Because if I draw this molecule without the double bond, and I've drawn all of the hydrogens that I've already put on the molecule, what's the issue with the two, the second and the third carbon here?
They don't satisfy the oxide.
Yeah, we need 4 bonds on carbon. They each only have 3. So what happens is that in place of the double bond, we just add hydrogens to the 2 carbons that the double bond was between. Right? So all this reaction does is it eliminates the double bond and adds hydrogen in its place. And so this is the type of question that you'll get for a predict the products, right? So it might be something like, here's an alkene, these are the conditions, what's the product going to be? And I might say name the reactant and name the product in this case. And if we were to name the reactant, this would be 2-butene, because we just did that one a little bit ago. And what's the product called? Right, I've drawn all these hydrogens, so it looks a little bit different. But is there any double bonds in the structure now?
Oh, no.
No, so what should the suffix be? Butane, right? So this is going to be just butane. Yeah, I was talking with Karsten and Chi a couple days ago, and some really fun organic chemistry questions that they said, well, you can have predicted products where you're just given the reactants. You can have retrosynthesis where you're given the product and then you have to find a way to get to the reactant. And then there's everyone's least favorite one where they just have two molecules and you have to write the conditions for what would actually get you there. There's a lot of ways you could torture students with this. And so with my 212 class, I'm kind of getting into a lot of that. With you guys, I'll be a little bit nicer. We're just going to be mostly starting with the reactant and then, you know, what's the product? Predict the product is the umbrella that this goes under. All right, any questions on this? No? Jennifer? Do you have a question? Okay. Okay, so why don't you guys if we have something like this, predict the product and name the reactant and the product for this reaction. Okay, so what's the name of this compound on the left here? What groups do we have on this compound? Or what, I'm gonna highlight the important parts of this molecule. We have the double bond. What else do we have? The chlorine, right? So we have a halogen and then a alkyl group, the methyl group, right? And then how are we gonna number this chain? From left to right or right to left? Right to left or left to right? It should be left to right because we want to put the double bond on the lowest possible number. So we put 1, oops. Go to, so it'll be numbered 1, 2, 3, 4, 5, 6, right? So the parent chain has 6 carbon atoms, so it's going to be what prefix? Hex, right? So that'll be hex. And then there's a double bond, so what's the suffix? Ene. And then it's on which atom? 2, right? So that's everything that's related to the double bond of the alkene, right? 2-hexene, parent chain is 6, so it's hex, and then 2, because that's where the double bond starts. And then what do we have on the, we have 2 other groups. We have a methyl group and a chloro group. Technically, which one's gonna go first? Chloro, why?
Comes first.
Because it's in a higher in alphabetical order priority, right? So then we're gonna have that on 4 chloro. And then what do we have last? Or what are we missing from our molecule? Yep, the 5-methyl group, right? So this will be 5-methyl, right? So we have 4 chloro, 5-methyl, 2-hexene. That's the name of this compound. After it goes through being exposed to hydrogen gas and a platinum catalyst, what's the molecule gonna look like? How does it change? Yep, we add 2 hydrogens, and where do they get added? What carbons? 2 and 3, right? So all we do when we're drawing this molecule is we just get rid of the double bond. Make this a little neater. Get rid of the double bond, and then everything else stays the same, right? So now we don't have a double bond anymore. The groups of interest are the methyl group and the chlorine group, right? Those are our substituent groups now. You don't have to draw anything else, right? If you want to draw that where the hydrogens went, that you can do that. I did that on this slide just because I wanted to, you know, reiterate that the hydrogen gas, what's actually happening when you're adding it is it actually adds hydrogen to a specific part of the molecule. I wanted you guys just to see that hydrogen goes there. But when we're drawing the carbon skeletons, we don't have to draw the hydrogens ever.
And how do you know that the hydrogens go on 2 and 3?
Because that's where the double bond was, right? So the theme with hydrogenation is we replace the double, and then I'll put in parentheses, or triple bonds with hydrogen. All right, so this is the theme of hydrogenation, is that we're eliminating the double bond and we're replacing it with hydrogen. Everybody might be able to see that. Does that make sense? So kind of the quick and easy way to do this is that I see a double bond, it's in these conditions, it's getting eliminated, and really all you have to do when you're predicting the products is you just draw it without the double bond. Right, if we think about all I did here between these two structures is I just drew this one and that one, I just didn't draw the double bond there. The hydrogens are implied, so you don't even really have to draw them. I just did it on the first example just to see that it's an addition reaction because we're actually adding hydrogen to the molecule. And so what's the name of this second molecule? Which way are we going to number it, from left to right or right to left? Right to left this time, right? Because we're going to put our substituent groups on the lowest possible number because there's no double bond anymore, right? The double bond is what took priority before. Now there's no double bond, so we number it the other way to put the methyl and the chlorine group on the lowest possible number, right? And so it'll now be 3-chloro, 2-methyl, and then what's the parent chain name now? Hexane, right? So this will be hexane, right? And we only use dashes to separate, and I forgot an O for the chloro, dashes to separate the letters and numbers, and if there's multiple groups of that type, we have to separate the numbers by commas and put a prefix before the group to indicate the number of that group. Oh, I forgot it for both? Yeah. Chloro. There. Does it make sense how hydrogenation works? Right, so the basic idea is how I just gave it to you. That would be the basic idea for how a predictive product scheme will work. And so for all the reactions we're going over, that's mostly what I'll do, is predict the products for how these predict the products for a reactant molecule given the conditions. Okay, so the next one we're going to be talking about is the halogenation of an alkene. So this happens readily. We don't need any catalyst, right? A catalyst like we had in the previous one, which was platinum or nickel. This happens without any catalyst, and halogenation means that we're doing what? It's an addition reaction, which means we're adding something. And what are we going to be adding most likely? Adding a halogen, and it's going to be eliminating a double bond to do so. A double bond, and it could also be a triple bond too. It can happen with both. And so if we have, for example, we'll start with 2-butene, like what we had before, and we add fluorine gas to this molecule. We're going to eliminate the double bond. In the spots where the double bond we're going to add a halogen across the double bond. One halogen on each atom. Same thing we do with hydrogenation. It's the same theme with halogenation. The only difference is that this does not require any catalyst. This is because halogens tend to be a bit more reactive than just hydrogen. Right, so this is what we've added to the molecule. We see that the double bond is gone, and now we've added 2 fluorine molecules. So if we were to name the molecule on the left, what we said, this is 2-butene, because we have a double bond on the second carbon. In the molecule on the right, what's that molecule's name going to be? 2, so we have a number. I'll put them right here. We have 2. And what else am I adding? Yep, it'll be 2, 3, dash, right? We're going to put, there's how many fluorines? So we need the prefix di. And then the name of the substituent group is fluoro. And then the parent chain is butane, right? And we have ane because we've eliminated the double bond. It's an alkane now. So this is how halogenation works. This is exact same thing as hydrogenation, except now we're adding a halogen across the double bond. And it happens readily because halogens tend to be a little bit more reactive. All right, so am I good to go on to the next slide? Or are you guys still writing? I'll give you guys a second if you're still writing. We'll give you guys an example of a predicted products for halogenation. Okay. All right, so why don't you guys work? To then predict the products, name the reactant, and name the product for this reaction. The name of this molecule we're starting with here. All right, we have cyclo. Why do we have cyclo? It's a closed ring. Closed ring. Pent, because why?
5 carbon.
5 carbons. In parent chain, which is the ring. And then ene, because there's a double bond. So you could also put 1 cyclopentene if you want. You don't have to, because it's a little redundant. Because whenever you number a cyclic ring, you always just start the highest priority functional group, which is the alkene in this case, at number 1, right? So we would number this 1, 2, 3, 4, 5. We could also number it 1, 2, 3, 4, 5, and those would give us the exact same structure, right? You don't have to put the 1. I like to put the 1 just because it really reinforces, the numbering of the group with the molecule, right? And so we add chlorine gas to this, right? And so this is a reaction that happens readily. And so what's the product going to look like? Are we still going to have a cyclic ring? Yep, right, because we only break what kind of bonds? We only break the double bonds, or we only get rid of the double bonds when we do hydrogenation or halogenation. And so we still have our parent chain of 5 carbon atoms, and then how does the structure change? We've gotten rid of the double bond, and what adds across the double bond?
Add the 2 carbons.
Yep, we just add the 2 chlorines where the double bond was. And we could number this 2 different ways as well. We could number it starting from 1 chlorine and go counterclockwise, or start from the other chlorine and go clockwise. And that'll give us the exact same name for both of these. So we have 1, 2, 3, 4, 5. And how do we name this molecule? 1, 2, dichloro, because we have 2 chlorine groups, and then it's going to be cyclopentane. Yep, cyclopentane.
Remember, like 1, 2.
Yep, it looked like you did a triangle there, but I think you meant 1. You went counterclockwise, right? Yeah, so you could also number it 1, 2, 3, 4, 5. Numbering it both ways is okay. Is that what you did?
Yeah.
Mm-hmm. Yeah. And if you did both of those numbers, you realize you get the exact same name.
I went 1, 2, 3, 4, 5.
You went. I'll draw this with the.
Oh yeah, well you have it as green. Right?
Yeah. So yeah. Okay, so there's the green and the red numbering here. Both of those are acceptable. Right. And like I said, there is a priority. I'm not going to be super strict about making sure that you have the perfect priority in alphabetical order, because I know it's a lot of stuff to keep track of. But it's because, right, the idea with the name is that you're just providing a map from the name to the structure of the molecule. So there's generally a number of different ways that you could actually get the structure from the name, right? There's a most correct way, but then there's other ways that are still acceptable in that they still work technically. Once you get to more and more complicated molecules, then it's harder and harder to do that if you're not going through the actual steps. All right, so we have 1, 2 dichloro because we have 2 chlorines. All right, so just to reiterate again, the 1, 2, these are the positions of what? Chlorines. Di is because there's 2 chlorines. Chloro, because there's chlorine substituent group. And then the cyclopentane, that's the same, right? Cyclo for ring, pent for 5 carbons, and then ane. Ane was what again?
Single bonds.
Only single bonds, right? Single bonds. Right, so that's how we break down the name of the structure, right? So the naming is supposed to give us a map from the structure to the name and vice versa. Okay, any questions on that? All right, so I gave you guys a little. I'll give you guys a little bit more complicated molecule, right? We've only done the linear molecules, and then I gave you a cyclic molecule here. But the idea is that no matter what the molecule looks like, you're doing the exact same thing, right? If we know the conditions, if I just gave you a halogen and there's an alkene, wherever that double bond is, you're just getting rid of it and adding 2 halogens where the double bond was. Okay. Do you have a question?
I actually remembered it different. I remembered it where the first chlorine is, right
Mhm.
at the top. I put 1 right there.
1.
And then I went 2, 3, 4, 5.
So you did 1, 2, 3, 4, 5, right? So can you tell me why this might not be the most correct way? Israel?
Because then you're gonna move the chloro to a higher number.
Exactly. You want the lowest possible numbers that you can have, right? And so here you still have the 1, but now you would have a 5 here. And since that's a larger number, it would technically be less correct. Like I said, I'm not gonna, it's not, you get the whole question wrong if you do that. It's technically not the most correct way, but you would get the same structure drawing that, right? So it still, in essence, gives you what you want the name to give you. But I mean, even I do stuff like that all the time. A lot of times if I'm trying to draw a molecule, or if I give you guys a name for a molecule before drawing it, sometimes then I realize the way I named it isn't actually the most correct way to name it, because there's a better way that you can count the chain and stuff like that. But if you're just starting from a name, that can happen pretty easily. Okay, all right, any other questions on this? No, all right. Okay, so the next reaction is the hydration, again with the typo. This is the hydration of an alkene. And so this one does not happen readily. You need strong acidic conditions for this to happen. And this is the addition of H2O to an alkene. And it's in the form of a hydroxy group. And all a hydroxy group is, it sounds fancy, is just an OH group and a hydrogen. Right, so we're not actually adding water, the molecule H2O, to our alkene. We're adding a hydroxy group, an OH, and a hydrogen, right? So the same way the last 2 ones, it was what we would call a syn addition, right? So that's not important, but it means that we added the same group across the double bond. A hydrogenation, we added 2 hydrogens. Halogenation, we added 2 halogens. Here, 1 carbon is gonna get an OH, and the other one's gonna get a hydrogen, right? So we're adding 2 different groups. And so,
Group,
hydroxy.
sorry. Hydroxy.
Yeah, and so we haven't talked about hydroxy or anything. I'm just introducing it now so you guys are familiar with it when we talk about alcohols. This is a hydroxy group, right? Whenever you have an OH group, meaning you have OH bonded to your hydrocarbon, it is called a hydroxy group. If it's the highest priority group, then it changes your alkane into an alcohol, right? So this is going to be the basis for what an alcohol is when we get to that. And so if we start from our trusted 2-butene, we're going to be adding water. So we need water, and we need acidic conditions, right? So that's where you have H+, that can be any acid, hydrochloric acid, sulfuric acid. And what's going to happen is we're gonna add an OH group across and then a hydrogen on the other spot. All right, so the water molecule, one part of the water molecule goes to OH and the other part is for hydrogen. But we still eliminate the double bond. And that's because these alkenes are more reactive than, alkanes which is why this reaction happens. And so the name of this molecule, and we haven't gotten to alcohols yet, this would be 2-butanol, right? The OL is gonna signify that it's an alcohol, right? So ene signifies double bond, adding an OL signifies alcohol. And then 2 is just the location of that group. But I wouldn't expect you guys to name that yet. We'll, hopefully in another hour you guys will be able to name that. Right, and you might ask yourself, well, how do I know where the OH goes and where the H goes, right? Because before is the same group you're adding. Technically, the OH group is always gonna go on the higher degree carbon or the more substituted carbon, right? So this I'm not gonna test you guys on. You're always just gonna be getting a second degree carbon, but where the OH goes is going to go on the higher degree carbon. So if we start from, let's say, this double bond versus this double bond versus this double bond, right? So these are 3 different alkenes that we have. We have our acidic conditions, and there's water present in solution. The OH in the first case is going to go in the middle, and the hydrogen is going to go on the edge, because that is a carbon that's bonded to more carbons, right? And the degree of the carbon is the number of carbons that the carbon is bonded to. Right, so we would classify this carbon as a first degree carbon. Let me write this on the, right here. So this carbon is a first degree carbon because it's bonded to one other carbon. This carbon is a second degree carbon because it's bonded to 2 other carbons. And this one is a third degree carbon because it's bonded to 3 other carbons. And so the OH group is just always going to go on the higher degree carbon, is basically the idea here. Like I said, I'm not going to be giving you anything where you're really going to have to think about this much, but this is just how it'll actually work. In the second case, the OH group could go on either, and that's because if you rotate this molecule around, you'll see that that's actually the exact same molecule. And then in the last case, right, we get rid of the double bond, and we wonder, does the hydroxy group go here or here? Well, this is the higher degree carbon, so the hydroxy group will be here. OH and then H. Right, and like I said, I'm not going to give you anything where you have to think about this, but this might be something that you thought about. Or if I did give you a challenging molecule on a quiz or an exam, that might throw you off because you're like, well, we never talked about where they go specifically. But like I said, I'm not going to be giving you anything where you'll have to be that concerned. And this just has to do with the fact that there's, in the intermediate of this reaction, as the reaction happening, there's a positive charge, and the positive charge is more stable on a higher degree carbon. Okay. So for this reaction here, since we can't really name the alcohols yet, I don't want you to name the product, but oops. H plus, H2O. Predict what the product would look like. We're not going to name them though. So what did the structure look like for you guys? So we still have our pentane ring, right? We still have one carbon coming up here, and what do we have to do here? We just add an H and an OH across where the double bond was. Right? We don't have to draw the H if we don't want to, so that would be acceptable. Here, the OH goes on the carbon on the ring because it's the more substituted carbon. But if you wrote this like that, that would be okay, just because I'm not worried about where the OH group actually goes. The most correct answer would be you would probably have something like 99% this in solution, and you'd have probably 1% of this as a byproduct of the reaction. Okay. All right, so let's take like a 12-minute break. We'll come back and we'll finish up unsaturated hydrocarbons, aromatic compounds, and then we'll get into organic compounds of oxygen and alcohols. Okay, so we just finished up hydration. We did a couple predict the products. I actually made that slide twice. So the next thing we're going to talk about for unsaturated are going to be alkynes. And so what do you guys think alkynes are going to be? Yep, unsaturated hydrocarbons with at least one triple bond. Hydrocarbons with at least one triple bond. And so these are also going to be sp hybridized, which means that these form a linear part of the molecule. Right, so these are going to be sp hybridized, so they're going to form a linear part of the molecule. In the same way a double bond is overlap of p orbitals, two unhybridized p orbitals, a triple bond is overlap of two different unhybridized p orbitals. So I drew this little picture here before, like this. These two are, let's say they already have a single bond to each other. The red, oops, that's not red. The red overlap represents the double bond existing, and then if they have two other unhybridized p orbitals and those have overlap, the blue represents another overlap between perpendicular p orbitals, and so that creates a triple bond, right? So you have the red is one extra bond, the blue is another bond on top of that, so total you have the single bond, one pi bond, and another pi bond, 3 bonds. That's why it's a triple bond, right? And so these are even more restricted, right? Movement, there's definitely no rotation for this bond. And also because it's linear, right? There's 3 bonds between each carbon. That means it can only be bonded to one other partner on each side to have 4 bonds total. These are going to restrict the structure of molecules by a lot. That portion of the molecule is going to be a linear portion of the molecule, right? Where you can draw a carbon skeleton and then you have a double bond there and there's still a kink in the line. For a triple bond, it'll look something like that for the same molecule. It's going to force that part of the molecule to be linear. Right, and so that's just the general idea of what a triple bond is. The naming for triple bonds is we replace the ane in alkane with ine. Right, so ine is going to be the suffix now whenever we have a triple bond. And then similarly to alkenes, we have a number and a dash to indicate the location of the triple bond. And the reactions for triple bonds are identical to those of alkenes. The only difference is instead of one hydrogenation, you'll have two hydrogenations. One halogenation, you'll have two halogenations, right? So these are very similar to reactions for alkenes. So we're not going to talk about reactions of alkynes because they're exactly the same as reactions for alkenes. And in a carbon skeleton, what a triple bond looks like is you just have 3 bonds like this. So this will represent 1, 2, 3, 4 carbon atoms here. Right, so the ends of these lines aren't necessarily new carbons for the above and below here. There's still only 4 carbons total in this structure. Sometimes you'll also see, one straight line going all the way through, and it'll still be 1, 2, 3, 4. And it's just kind of hard sometimes to visualize that because in carbon skeleton, the kinks or edges of lines represent carbons. When you have a triple bond, it makes the structure linear, which means inherently there is no bends or kinks in the line at that point. All right, any questions on the naming or anything? We'll go over an example, but how that works, but. Okay, so try naming the following compound. The structure is drawn a little funky because as I said before, I had a really good software to draw organic molecules, but it would actually look something like this. Would be probably a more accurate way to draw this molecule. Just take a second, see if you can figure out how to name the molecule. Again, everything else is the same. The only thing that changes with the triple bond is now we have "-ine" as our ending here. Right, how many carbons are in the longest chain in this molecule? We have 1, 2, 3, 4, 5, right? So we have 5 carbons, so the prefix should be pent, right? We have pent. And then what should the suffix be here? "-ine", right? Because there's a triple bond, and it's on which carbon? 2. It starts on carbon number 2. And then what groups do we have here? We have 2 bromines, right? So we need to indicate that there's 2. So we put a prefix "di" in front of bromo. And then what about the numbers? What do we put for the numbers? We put 1, 1, right? Because they're both on the first carbon, and we separate numbers by commas, right? So we separate numbers by commas, numbers from numbers, and we separate numbers from letters by dashes in the name, right? So this is 1, dibromopentyne. Jeff?
So in this one, writing 1 wouldn't be redundant since there's 2 of them?
Yeah, since there's 2 of them, we need to indicate the location of both of the bromines in this case, right? So usually the 1 being redundant is only when you're talking about the overall type of molecule you're dealing with. If you're ever specifying the location of a substituent group, you're usually going to write 1 for that. It would be, for example, if there's an alcohol and the alcohol is on the first carbon, then you don't have to because the molecule itself is classified as an alcohol, right? Whereas this one is classified as an alkyne, so if the triple bond is on the first carbon, you wouldn't have to specify that. But since it's an alkyne, it's not an alkyl halide, meaning that this doesn't define what the molecule is. We have to specify exactly where those groups are. Short answer to that is if it's a group on it and not the type of molecule itself, you have to write all the numbers. Good question. Okay. All right, so here we're going to go the other way. right? So we've gone a lot from here's the structure, what's the name, here, draw the carbon skeleton for 1-fluoro, 3-iodo propine. Okay. Let's go through and break down the name. Prop means what? 3 carbons in the parent chain. Ein means triple bond, right? Iodo or 3, let's see, 3-iodo means, yep, an iodine, iodine on 3rd carbon, and then 1-fluoro means fluorine on 1st carbon, right? And so there's 2 ways you could draw the parent chain here. I wouldn't, one is correct and one's not, but I'm not gonna mark you down if you do this. If you just want to, if you were writing quick during an exam or something, and you did something like this, that would be okay with me. I wouldn't mark you off for this. Technically, this is not the right geometry because this is a linear molecule, right? So technically this is the more correct way to draw the triple bond starting on carbon 1. But because we, I think it's sometimes hard to realize that this is 3 carbons right here. So I'm okay if you draw the first one, right? Because this would be 1, 2, 3, and here it's the same thing, 1, 2, 3. So we have 3 carbons in our parent chain and a triple bond on the 1st carbon, right? Since it's sp, that means that for each carbon to have 4 bonds total, this needs to have 1 other bond. What is the other bond going to be to here? It'll be to fluorine, right? Because fluorine is on the 1st carbon. Yeah, so it's 1-fluoro, so fluorine is going to be bonded to this carbon here. And then on the 3rd carbon, we'll have what, everybody? Iodine, right? So the iodine will be on the 3rd carbon. So that's what this molecule looks like. It's kind of a funny looking molecule because it's a triple bond. We don't have to put the 1 for propine because the triple bond's on the 1st carbon. You could put this, the name for this could also be 1-fluoro, 3-iodo, and then another dash, 1-propine. That would also be acceptable to put that. Right, all we did here is we just specified the location of the triple bond. It's implied here because it's not written, and it's also for a propine. If the triple bond was here or it was there, that's the exact same molecule because you just flip it around. Really what's defining the 1 and 3 carbon here is what groups are going to be on them. Okay, any questions on that? All right, so the last thing we'll talk about for unsaturated compounds are aromatic compounds. And so aromatic compounds are going to be something like benzene, which you may have seen before. So benzene will look like a cyclohexane with 3 alternating single and double bonds. The other way you'll see it drawn sometimes is it'll have a circle in the middle, and this circle has to do with the fact that benzene is an aromatic compound. And so aromatic compounds are typically low in reactivity. You have to have special reaction conditions to get them to react. So they're relatively inert, which makes them good solvents for reactions to happen because they can kind of hold things in liquid phase without interfering with the chemical reaction. And they typically are nonpolar, right? Because hydrocarbons in general are nonpolar and hydrophobic. Right, so these are liquids. A lot of times aromatic compounds can be liquids. These are liquids that will be separate from water if you mix them together. And so I think you guys saw a little bit of this on the day where we looked at mixing a couple different solutions. We did have some organic solvents there. Benzene would be one of them, and it will separate. It'll be a clear separation between water and benzene. And so this aromatic character is generally indicated by alternating double bonds and single bonds. So in benzene here, for example, that's what we have. We have alternating single and double bonds. Between each double bond, there's a single bond in between them. And that's not all you need for it to be classified as aromatic. This is what's defined as conjugation, right? So this alternating and single double bonds, single and double bonds. This is what's defined as conjugation. So when you have a conjugated pi network is what it's called in an organic molecule. It's alternating pi bonds and sigma bonds. Really what you need also for aromaticity is you also need it to be a ring structure. It also needs to be cyclic, and there's special rules to define if the molecule is aromatic or not. And one of them is that it needs to be cyclic. And the reason that all of these properties fall out of aromatic compounds is because when you have these alternating single and double bonds in a ring structure, what happens is those electrons that are in the double bonds, in those unhybridized p orbitals, they become what we say are delocalized, meaning they're not actually existing just in that bond, right? So these electrons, the electrons are delocalized. And does anyone know any other examples of real world material where electrons are delocalized?
Like rust?
Hmm?
Like with rust?
So with rust is on something that where electrons are delocalized. The rust layer, actually, they do end up localizing them, and then it makes a very stable structure, which is why it forms in the presence of oxygen on top of them, right? So where else do you think electrons flow freely in real world material? Certain types of gases, so you could have an ion gas, and electrons, like in a plasma, like on the surface of the sun, that could be something. What about something you guys use a lot every day?
Electric wire?
Yeah, wires, right? So metals is where electrons are actually delocalized, right? And that's what you need for electricity to conduct. You need electrons to be able to flow. And so in these organic molecules, when you have these cyclic structures, the unhybridized p orbitals creates a network that these electrons are just moving around in between. So they actually have like little, rings of current that are generated on these tiny little molecules. And you can actually use these in polymers and stuff to make plastics that conduct electricity. And everything is conducted through this delocalized pi system. And when electrons are delocalized, it also lowers the energy of the structure. And so that's what makes them very stable and unreactive, right? So you can do some tests, and actually we talked about one of the tests is you can test how hard it would be to halogenate or hydrogenate a molecule like this, and the energy of performing the hydrogenation reaction, that tells you how much energy you have per double bond, roughly, right? And you find that for these molecules, the energy per double bond is actually a lot lower than what you would expect, so meaning that there's some other weird phenomenon that's going on that's stabilizing these structures. And that what it ends up being is that these conjugated networks in a ring have these delocalized electrons that then give the molecule its own special properties. And so you can kind of think of it as a tiny little current that's being generated on top of these molecules, and that's what makes them so stable and so nonpolar and hydrophobic as well. And so these are what aromatic compounds are going to look like. Generally, they're going to be ring structures. Sometimes you can have something where there's a lone pair. So if you have a molecule like that, that can be an aromatic compound, for example, because the lone pairs there exist in delocalization around this alternating single and double bond, even though there's a heteroatom there, right? So aromatic compounds are kind of interesting. And so a lot of people, especially someone in here has a Z flip, right? The phone. Did I ask that last lab too?
Yeah.
Dang, okay, so this is my other class. Someone has a Z flip. But the Z flips use organic electronics, right? Because when you touch your phone, there's a little half capacitor there. So you need to be able to conduct electricity, and the Z flip has to be flexible at the same time for the phone to be able to fold like that. And so you have to use organic electronics for that, because metal is, not super ductile in the sense that if you keep deforming it, eventually it'll break, right? So plastics don't have that irreversible deformation. So that's where we see some aromatics in everyday use for electronics and stuff. And these are more and more popular. Okay, all right, so that'll conclude everything for unsaturated hydrocarbons. So everything we talked about should be on the exam next Tuesday. We'll end that here, and then we're gonna go on to
The last example you gave us, why is it that the triple bond is closer to the fluorine instead of the iodine?
because the iodine is on the third carbon.
Right.
The triple bond is closer.
Mhm.
How do you mean it's closer?
It's closer to the first carbon than the third carbon.
Right, the fluorine is on the first carbon,
Yeah.
and the iodine is on the third carbon.
Why is the triple bond closer to the first carbon?
Oh, because the one isn't, so the one, that's a good question. So the one isn't explicitly written, but because we have, this is another way that we could write the name right here,
Oh,
right? And with this, we explicitly say that the triple bond starts on carbon one. Because the one isn't written there, it's implied that it starts on carbon one.
Are you likely to do that?
Hmm?
Are you likely to do something like
I'll usually, if I give you the name of something, if I don't put the one there, it's usually because I forgot to put it, but I would give you the one just to kind of emphasize that it would be clear where everything is. Like I said, it's technically fine both ways, but I like to have the one there because it makes more sense in my head that that's, the rules, so we have to follow them. Last one?
posting, on the study bank?
Yeah, I'll post the practice exam like I usually do. So that'll be posted. I have most of it done, so it'll be posted by tonight. So you have a week to look at it. And I'll probably do like an extra office hours again next Sunday. I'm watching my mom's dogs this weekend, so I get the